Assalamu alaikum. So what I'm going to do in this video, so using Python, using scipy.integrate, inside the scipy.integrate we have this function solve IBP. So using this function I'm going to find this first order equation. I want to solve the first order differential equation, and then I'm going to solve the second order differential equation. Okay, so let's start. So first of all, let's say I have a differential equation that looks like this, and here I may have different things. Let's say in my code what I have 5y60. So let me write here 5y plus 60. So this is my differential equation, and my goal here is to find y. So how to find this thing? And in the question I may be given the initial condition, and let's say the initial condition is 30. Okay, so what I'm going to do, I'm going to use here RK45 method. So RK45 method, you see it here, the method is RK45 method. Okay, so let's start. So inside, let's focus here solve IVP. So you can see that this solve IVP is taking a function f. So this is the function I have written here, which is taking t and y, and you can see that actually this part is actually f, and it is the function of t and y. So it is taking t and y and finding the dy by dt, I mean dy by dt, 5y plus 60. So this is 5y plus 60, and returning that dy by dt to the solve IVP. Okay, then we have t span. You can see what is t span. This is the from starting time to the ending time, and in my case starting time is 0 and ending time is 0.2. So you can see that the starting time is 0 and ending time is 0.2. You can change it, let's say from 1 to 2. So you can see that starting time is from 1 to 2. Okay, let me take it to initial condition, initial state, and then you have this initial condition. You see, why not, this is the initial condition, and initial condition is 30. That's why my graph starts from 30. So if you write here 50, then your graph will start from 50. Okay, so now method is RK45 and t evaluation. So what is t evaluation? Let me tell you it later, but after running this code, you see, let me show you what is inside solve. So inside solve we have many things, but we have to focus here t and y. So how to access this t? Simple, solve.t. So here you have the time. So you see you have 2000 samples of time. And why 2000 samples? Because t evaluation has 2000 samples of time, and you are sending t evaluation by np.linspace from starting to ending position, and the number is basically 2000. And how you are getting this number? You are getting this number from here, from this equation. So let me show you what is n. So you see the n is 2000, and you are giving 2000 samples of number. Let me show you this thing. So you see this thing is giving you the 2000 sample of number, and you are giving this 2000 samples of number to solve IVP and telling it to find the value in this time, and that's why you have solve.t 2000 samples of time and solve.y comma 0, and you have the output value in that time. You have 2000 time and 2000 output for that specific time. And what happens if you don't use here t evaluation? Let's see. So now you see your graph is not so smooth, and if you try to find solve.t, you see only this solve IVP function is only working with this 3 times. So it's simple that you will not get good result. So it's better to send your specific time sample. Okay, so let's again see what is solve inside this solve. So you can see inside this solve you have many other things, right? Number of function evaluation, that means how many times this function has been called. Then you have other things that is not needed for this time. Okay, so now you have take this time, take the value of output, and then you have plot, and let's see how the plot looks like. So this plot looks like simple. Okay, now let's work with the second order equation. So basically your second order equation looks like this. So it is a simple harmonic motion with damping. Obviously you have applied a force here, let's say a spring, and there are some damping here. Mass is m, spring constant k, damping is d, damping is, let's say, c. In my code I have written here as c, but that's not a problem. And you have applied a force here, and this is a periodic force, f naught cos omega t, just to give you an example. And if you write the differential equation, so your goal is to write any natural phenomena into a differential equation. And it is the beauty of differential equation that if somehow you can explain any nature by the differential equation, and boom, you obtained all the thing. You don't need to solve mathematically find the equation, just you have to find the differential equation. So let's say the position is x, the position of this object is x, so d square x by dt square. So this term has appeared for damping, and this term has appeared for spring, and this is the force. Okay, so now how I have to modify this equation to face that into the Python code. So what I will going to do, I will use here a state space model. State space model is very simple. You have to just define some variables. One is x1 and another is x2. So let's see what is x1. So I'm going to assume that x1 is x, simple, and x2 is dx1 by dt. Okay, I'm going to assume this, that x1 is x and x2 is dx1 by dt. Okay, now let's see. So let me start with here. So what is dx1 by dt? It is simply is equal to x2. Okay, so this is my first equation, and my goal is to write the differential term at the left hand side and write this kind of term at the right hand side. Okay, let me give you another. Now my goal is to find dx2 by dt. So how to find this thing? I have to write this equation here, but with some modifications, that m d square x by dt square, then this is f naught cos omega t, then I have to take this all part at the right hand side. Oh, this is not y, this is actually x, sorry. So c dx by dt, then minus kx. Okay, and then let's divide by m. Okay, so you can see that I have done this here. Okay, let me first finish the equation. So now you can see that this is d square x by dt square. So I can write it like this, d by dt dx by dt. And what is dx by dt? You can see that x is equal to x1. So let me write here x1. And what is dx1 by dt? It is basically x2. So let me write here x2. Now f naught by m, it's okay. C by, what is dx by dt? X is basically x1, and you can see that dx1 by dt is x2. So let me write here x2. And what is x? X is basically x1. So let me write here x1. So you can see that I have two equations, and the common format in these two equation is, at the left hand side I have the differential term, and at the right hand side I have x1, x2 and the input. So force is the input, right? So you can see that at the left hand side I have the differential term, and at the right hand side I have input and x1 and x2. Similarly for this, you can assume that here you have 0 into x1, right? Then 0 into input. So this is the format actually. So at the left hand side you have to write the differential term, and at the right hand side you have to write the input and all other variables. Same thing for the 3, 4, 5, fifth order, etc, etc. Okay, so let me implement these two codes in my code. Okay, so you can see that the damped oscillator function now, and this damped oscillator function is called from here. So this is the damped oscillator, solve IVP is calling this damped oscillator function, and it is taking t, similarly time, and the x. So what is x? Now x has two things, one is x1 and another is x2. Then I have found the dx1 by dt, this is simply this equation, and then I have written this, which is basically this equation, and then I have written this two derivative term, and rest of the thing is same. You can see the initial conditions. This one, the first one, is the initial condition of first variable x1, and this is the initial condition of the second variable x2, and then I have fetch it to here. This is the initial condition. Then what is t span? Similarly, from start to ending time, method is LSODA. Okay, let me show you one thing, that there are actually many methods. Previously we have used RK45, and now I have used LSODA, and I have also other methods, right? RK23, this is RK25, 45, this is RADAU, LSODA, PDF. So you can use any of the methods you want for the basic level actually. So I'm using now LSODA, or you can use RK45 as well. The anti-evaluation, all the things are same. And now if I run this code, so let's see what is inside sol. So similarly inside sol you have time, but now you have 2y. Y means the output. So now what is the goal? Your goal is to find this x1 and x2, right? And yeah, that this sol contains two output, one is x1 and another is x2, because you can see that you have two variables, x1 and x2, right? So how to approach, how to get access to the t? So sol.t, it will give you the time, and if you write sol.y then 0, then it will give you the x1, the values of x1, then sol.y will give you the values of x2. Okay, so you have obtained x1 and x2, but what is x1? X1 basically the position, right? So this is the position of this block. And what is this? If you differentiate the position, you will get the velocity. So x1 is position and x2 is velocity, and you can see that. Then I have plot this thing here. This is actually position and force plot versus time, and this is the power plot. So what is power? Power is basically force into velocity. So actually I am in the resonant condition. You see that I am in the resonant condition. You see the omega root over k by m. For this frequency my system has gone to the resonant condition, and you can see that power is always positive. That means always giving power to the force, is always giving power to the system. But if I mismatch something, like let's say if I break the resonance, and then let's see what is the, oh, now you can see the power sometimes positive and sometimes power is negative. That means force is sometimes giving power, sometimes taking power. That means, that power is 0. So this is the method of finding solving differential equation with code. Okay, so now let me solve another third order equation. So let's say let's write here t, then d square y by dt square, then let's write here 5y 65y dy by dt, then let's write here sine t y, and then let's write here e to the power t. Okay, so this is the equation, and now our goal, sorry, this is not x, let's say this is y. Oh no, sorry, this is x. Okay, so now how I'm going to find this x. So to find this x, I have to again derive some variable. Let's say x1. X1 is x, and what is x2? This is basically the, let's say, dx1 by dt. And what is x3? This is the dx2 by dt. So you can see that as my order is 3, so I have defined 3 variables here. So let's work with the first. So you see that I have obtained the first equation, dx1 by dt is equal to x2. This is the first equation, and dx2 by dt is equal to x3. This is my second equation. So yeah, so now I have to make another equation from this. So let me rewrite this thing. Let me put d cube x by dt cube and take all the thing at the right, e to the power t minus 6t d square x by dt square 5. Oh, this is not y, this is actually x. So 5x dx by dt, and then let's write here x sine t x. Okay, so now let's modify this thing. You can see that d cube x by dt cube. So what this thing is, so x is basically x1. If you take a derivative once, it you will get x2. If you again derivative, you will get differentiate, you will get x3. And if you again differentiate, you will get dx3 by dt. So this is basically the dx3 by dt. Then I have here, okay, I don't want to write it again. Let me write here dx3 by dt. Then this is e to the power t 60. Then what is d square x by dt square? You can see if you differentiate it twice once, then again you will get x3. So this is basically the x3. And what is this? Dx by dt. If you differentiate x once, you will get x2. So this is basically x2, right? So x2, and then x. So x is equal to x1. So let me write here x1. So I have obtained 3 equations here. Okay, so let's modify our code. Okay, I did some mistake here. First of all, here I have to write minus, and here x is basically x1. So let me write here x1. Okay, so now I have written the code here. You can see. So this is my code. So now I have 2 variables here, x1, x2 and x3, and the function is f, which is called from here. Code is basically same as the previous, but the difference is you can see that dx1 by dt is x2, dx1 by dt is x2, then this thing is equal to x3, this thing is equal to x3, and then I have written the whole equation here, and then I have written the derivative part, and then the rest of the part is same. The method, let's say RK45, or let's say RK23. Let's see what happens. And then if I run this code, something problem here, right? Let's see. Let me run only this part. Something, oh, x naught. So initial condition, so as there are 3 variables, so let me give here another initial condition, 3 initial condition for x1, x2 and x3. Now let's see. Oh, it's taking a lot of time. Okay, so I have reduced the time from 0 to 10 only, and then I have run this code and I have found this kind of result. Okay, now let's see what is inside solve. So inside solve, again I have time, but now I have 3 outputs. One is x1, x2 and another is x3, And then let's plot this thing. Let me erase all the thing here. Okay, so what is x1? It is basically the sol dot y comma 0. And now let me copy this up. Sorry, let me copy this thing. This is x2. Here you have to put here 1. This is x3, and you have to put here 2. Then also you have time, which is sol dot t. So you will get t x1 x2 and x3, and then you want to plot, right? So plt dot plot. So t comma x1. So x1 is basically the position, you see. X1 is basically x, what you want. So let's plot this thing. Okay, so this looks like this. If I write here plt dot grid. Okay, so this looks like this. If I set an initial condition, this starts from 10. And what about x2? x2 increasing. What about x3? It's also increasing, but some oscillations here. Okay, whatever. But you got the idea how to solve this thing. But why this is increasing? I think for exponential part here, let me write here minus, and let's see what. Oh, okay, if I change the function, now you can see that what is x1. Let's see what is the position. So position looks like this. If I increase some the time, that's the 30. Oh, it's damping. It's, let's take here 50. So it's approaching to maybe 9.7, 9.73 or 4. Let me take 50 to 100. So you can see the function looks like this. It's approaching to a value around 9.73, but whatever. So this is the way to solve differential equations with scipy. Thank you. Stay with us.